Hey there, welcome to video number 18. Today we're going to discuss bipolar power supply biasing arrangements. Alright, let's start by looking at the power supply itself. What we've got is basically two DC sources connected in series, and the junction between the two is designated as our 0-volt ground reference. The top node is labeled VCC, that's our positive supply rail. This bottom node is labeled minus VEE, that's our negative supply rail. The total supply voltage we have to work with is just the sum VCC plus VEE. Now let's assume we've got this supply or something equivalent connected to our circuit over here. And let's start out by determining the cutoff and saturation values for this thing. Alright, remember when the transistor is in cutoff, ICQ equals 0. The transistor is acting like an open circuit from collector to emitter. So with no current flow, we've got no voltage drop across RC, no voltage drop across RE. The entire supply is dropped across the transistor. So we end up with VCE in cutoff equals VCC plus VEE. All right. Now in saturation, the transistor is acting like a short circuit from collector to emitter. So the only thing limiting current flow from the positive rail to the negative rail is RC and RE. So our collector saturation current is VCC plus VEE divided by RC plus RE. Okay, now pretty simple extensions of the equations we've derived previously. We've just got this extra voltage term in the numerator here and up here in cutoff. All right, let's clear the board and determine our Q point expressions. All right, to determine ICQ, we're going to work down around the base emitter loop with RB, VBE, and RE, and we've got our bias voltage applied down here, and it's a pretty straightforward process to determine that ICQ for this circuit is equal to VEE minus VBE divided by RB over beta plus RE. All right, this is derived basically the same way we've done it for all the previous circuits. The only difference is we end up with VEE up here instead of VTH or VB. All right, VCEQ. Well, let's see, we've got a total potential from top to bottom of VCC plus VEE, and we're just going to subtract off the drop across RC and the drop across RE. So VCEQ is VCC plus VEE minus ICQ times RC plus RE. All right, and that's all there is to it. It's really a pretty straightforward extension of what we've done before. Now, I'm going to clear my chicken scratch off of here and drag over nicer versions of these equations for reference purposes. So if you wanted to, you could take a screen capture here and you will have the circuit and its analysis equations handy. All right, let's do an example problem. All right, now we've got our circuit with a bipolar plus and minus 15 volt supply, and let's assume that beta equals 100. That's going to be our normal assumption unless there's some reason, compelling to do otherwise. All right, let's start out by finding VCE cutoff and IC sat. VCE cutoff, pretty simple. It's just the sum of the two supply voltages, ignoring that minus sign. So we've got 15 and 15, which is 30 volts. All right, the collector saturation current, IC sat, is equal to VCC plus VEE, 30 volts, divided by RC, 2.2K plus RE, 4.7K. Crunching through these numbers, what do we get here? About 4.3 milliamps. All right, so let's record that here, 4.3 milliamps, and I'll write them on my load line here as well. 4.3 milliamps IC SAT, 30 volts for VCE cutoff. All right, now let's do our Q point analysis. Clear this work out of the way. And ICQ equals VEE minus VBE divided by RB over beta plus RE, right? So 15 volts minus 0.7 volts is 14.3. All right, RB is 10,000 divided by 100 is 100 ohms plus 4,700 ohms. So our denominator is 4,800 ohms, and that gives us an ICQ of pretty darn close to 3 milliamps. All right, so I'll leave this here for a second. The equation, plugging in the numbers from the circuit, doing the arithmetic, 3 milliamps. All right, let's clear this and find VCE. All right, VCEQ is equal to VCC plus VEE minus ICQ times RC plus RE. All right, so we've got 15 and 15 is 30 volts minus 3 milliamps times 2.2K plus 4.7K. All right, and again, crunching through these numbers, we get about 9.3 volts for VCEQ. All right, the equation, substituting the numbers, grinding the arithmetic, 9.3 volts. All right, and I should have recorded my ICQ before. It was 3 milliamps, 9.3 volts. And again, I'm going to clear out my workspace here. And let's take a look at these values. Now, I've never asked for these before, but what we've got is the collector voltage with respect to ground, VC, at the Q point. So measuring from here to ground with the DMM, what would we see? Likewise, this is the emitter voltage with respect to ground at the Q point, and the base voltage with respect to ground at the Q point. All right, we're going to determine those because they're pretty handy for making quick, easy measurements in a circuit and for troubleshooting purposes. So how would we find the collector voltage? Well, the easiest thing to do is just to subtract this voltage drop from the positive rail. That's IC times RC, right? So VCQ equals VCC minus ICQ times RC. And in this case, we've got 15 volts minus 3 milliamps times 2.2 k ohms. And again, crunching through the math, we get 8.4 volts. So if we were to measure from collector to ground, we'd read 8.4 volts. All right, I'll write that in here. All right, what about from emitter to ground? Well, let me draw this drop in here. That's IC times RE. And if this node is at minus 15 volts, then the emitter must be this much more positive than the supply rail. So VE at the Q point, let me do that up here, is equal to minus VEE plus ICQ times RE. And we get minus 15 volts plus 2 milliamps, or I'm sorry, 3 milliamps times 4.7K. And if we crunch through those numbers, 3 mils times 4.7K, and we get minus 0.9 volts. Okay, let me make this a little nicer to look at. Okay, that's supposed to be 3 milliamps. All right, so we've got negative 0.9 volts sitting at the emitter with respect to ground. Now, just as a sanity check, we know that VCE is really shorthand for VC minus VE. So that should be equal to 8.4 volts minus VE, which is negative 0.9 volts. And 8.4 minus 0.9 is 8.4 plus 0.9, and that is 9.3. So we get a consistency check here, 9.3 volts for both of these. All right, lastly, VB at the Q point. Well, the base is 0.7 volts more positive than the emitter, so VB at the Q point is simply VE plus VBE, right? So that's negative 0.9 plus 0.7 volts equals negative 0.2 volts. So our base is sitting at minus 0.2 volts with respect to ground. All right, let me get this clutter all out of the way so that we can just look at the results. All right, so here are all of our Q point values, VCE, IC, and the other node values for the collector, base, and emitter. So let's fill these in on the load line. 9.3 volts is roughly a third of the way over here. That looks about right. So here's 9.3 volts. Q point, and that is 3 milliamps. Right, so there's our Q point. Now, is that a good Q point? Is it stable? Well, remember we want beta times RE to be really big compared to RB. And in this case, beta is 100, RE is 4700 times 100, that's 470K, which is much, much greater than 10K. In fact, it's a 47 to 1 ratio. So yeah, we've got a really stable Q point. We could stick just about any transistor in here and it's going to come up right on the money. All right, now we're going to do a variation of this circuit, and what we're going to do is add a voltage divider to the base network. All right, now we're still biasing up from the negative supply rail, but this time it's the voltage drop across R2 that's actually forward biasing the base emitter junction. All right, and we're going to have to do Thevenin's theorem on this network to derive an equation for ICQ. And here is the equivalent Thevenin network for this biasing arrangement. We've got the VEE source driving R1 and R2 that form a voltage divider. VTH is the drop across R2. So the equation for VTH is simply VEE times R2 over R1 plus R2. All right, and looking into the Thevenin equivalent, we see a Thevenin resistance that's simply R1 in parallel with R2. All right, straightforward enough. To determine ICQ, we just apply the same techniques we've done many times before, and what we're going to end up with is ICQ equals VTH minus VBE divided by RTH over beta plus RE. Okay, and it should be pretty clear where that all comes from if you've followed through all the previous videos, right? This is simply a voltage divider on the base, and we've got VTH, the drop across R2. RTH is the resistance looking into the divider from the perspective of the base. And there's our expression. VCEQ is the same equation as the previous circuit. We've got a total potential difference of VCC plus VEE minus ICQ times RC plus RE. This voltage divider network on the base does not affect this expression at all. All right, let me bring these equations over in a nice neat form for your reference purposes. Okay, clear this chicken scratch out of here, and I'll come over here and grab the equations. And here they are. All right, now I didn't go through the derivation of IC sat and VCE cutoff. They're the same as before, right? The collector saturation current is just VCC plus VEE divided by RC plus RE, and VCE cutoff is VCC plus VEE. All right, let's apply these to an example problem. And here's our circuit. All right, let's start off by finding our cutoff and saturation values, okay? VCE cutoff is simply the sum of the supply rails, which is 15 and 15, again, 30 volts. IC sat, well, I'll write it down. Since it's a little more complicated than VCE cutoff, it's VCC plus VEE divided by RC plus RE. So we've got 30 volts divided by 8.2K plus 1K is 9.2K. And that gives us, what, IC sat, about 3.2 milliamps. All right, so 3.2 milliamps. All right, and 30 volts here as well. Okay, let's clear the boards and find our Q points. All right, ICQ equals VTH minus VBE. Oh, we got to find that first, right? Well, VTH equals VEE times R2 over R1 plus R2. So that's 15 volts times 2.2K divided by 10K plus 2.2K. And that all works out to be about 2.7 volts. All right, RTH is R1 in parallel with R2. So that's 10K in parallel with 2.2K, which is about 1.8 K ohms. All right, so there's our VTH, 2.7 volts, 1.8 K ohms for RTH. All right, now let me get this mess out of here and we'll calculate ICQ. Jumped ahead of myself a little bit there. All right, ICQ, remember, is VTH minus VBE divided by RTH over beta plus RE. All right, VTH 2.7 minus 0.7 is 2 volts. RTH is 1800 divided by, we'll assume our beta equals 100 again. So 1800 divided by 100 is 18, plus 1000 is 1018 ohms. All right, so that gives us an ICQ of 1.96 milliamps. Let's just call that 2 milliamps. All right, so this circuit is going to have ICQ of about 2 milliamps. All right, clearing my workspace. Let's find VCEQ. VCEQ equals VCC plus VEE minus ICQ times RC plus RE. All right, so again, 15 and 15 is 30 volts minus 2 milliamps times 8.2K plus 1K is 9.2K ohms. So crunching through those numbers, we get VCEQ of about 11.6 volts. Okay, 11.6 volts. All right, so far so good. Now remember, our NPN transistor always has to be in the first quadrant, so VCE has to be greater than or equal to 0, and IC has to be greater than or equal to 0. So we look good. We're in the first quadrant where we're supposed to be. All right, now I've asked for the collector voltage with respect to ground, emitter, and base with respect to ground at the Q point as well. So let's find those. All right. Okay, VCQ we know is VCC minus the drop on the collector resistor, so it's VCC minus ICQ times RC. All right, so we've got 15 volts minus 2 milliamps times 8.2 k ohms, and that works out to be negative 1.4 volts. All right, now that might look kind of weird. Holy cow, we've got a negative collector voltage, but let's not worry about that yet, okay? We'll do a sanity check on this in a few minutes. Let's find VEQ. VE at the Q point is equal to what? VEE with the negative sign, right? Because we're going up from negative 15 to the emitter, and we're going to add this voltage drop by IC times RE. So it's going to be negative VEE plus ICQ times RE. All right, so that's negative 15 volts plus 2 milliamps times 1 k ohm. 2 mils times 1 k is 2 volts, so that's minus 13 volts. So our emitter is sitting at negative 13 volts with respect to ground. All right, let me record these up here. We had minus 1.4 volts at the collector and minus 13 volts at the emitter. And let's do a sanity check, because we know VCE equals VC minus VE. So VCE is negative 1.4 volts minus negative 13 volts, and that works out to be positive 11.6 volts. So we've got to check VCE is consistent with these values. All right, finally, the base voltage, VB, at the Q point is equal to the emitter voltage at the Q point plus the VBE drop. So we've got, what was VE? Negative 13 volts plus 0.7 volts is negative 12.3 volts. Negative 12.3 volts. So there are all the voltages that we could measure in this circuit, right? We've got 11.3 from collector to emitter. The collector is sitting at negative 1.4. The emitter is sitting at negative 13, and the base is sitting at negative 12.3. All these negative voltages are not a problem, because when we put it all together, we're still operating in the first quadrant where an NPN transistor has to be if it's in the active region. All right, so finally, let me sketch my Q point. All right, 2 milliamps and 11.6. That's roughly here. And here. And is that a good stable Q point? Well, let's do the last calculation. Beta times RE is 1,000 times 100, which is 100 k ohms, and RTH is 1.8 k. So we've got a ratio here of about 56 to 1. That is a very, very stable Q point. All right. So there we've seen a couple examples of variations on biasing arrangements, and in this case we've got bipolar power supplies. There are others, but these are two of the big ones. What I'm going to leave you with is a variation of these for you guys to do the derivations. Okay, so you want to find the equations for whatever is necessary to find IC sat, VCE cutoff, ICQ, and VCEQ. Okay, and that's it for today's video. I will see you next time.